A little while ago we were talking about acid rain, and one of the things we talked about in that topic was not just what acid rain is and what the problems caused by, but some of the, let's say, the debate or the political wrangling that went on in order to do something about the problem. So today we're going to talk about the ozone layer, and again, the ozone layer was not something that you hear about much in now, but when I was in high school, it was one of the big things that we talked about in terms of environmental challenges. So what we'll see is that some of the same strategies that were at play, or some of the same arguments that were played over the ozone layer, are at play in our current environmental debate. So anyway, let's talk about ozone so we know what's going on with it. Ozone is a form of oxygen, highly reactive form of oxygen, that is 3 oxygen atoms combined together to make O3. It can decompose quite explosively. It can be a problem. So you don't have large containers of ozone sitting around. It's also toxic to people. So as much as we want the ozone layer to be healthy, we don't want ozone to be around us. However, we can use it in small concentrations, right? There's no such thing as a safe chemical, no such thing as a dangerous chemical. There's safe ways of using them, and there's dangerous ways of using them. So we can safely use ozone in water treatment or wastewater treatment, or in fabric bleaching, because it's safer than chlorine bleach. We can also use it in the manufacture of some pharmaceuticals. Now, it's not in the pharmaceuticals, like you can't chomp on a bunch of pharmaceuticals and get some ozone, but it's used in the manufacture of it, somewhere along one of those steps. Okay, I said ground level ozone, or ozone around us right now, is a problem. What is it and how do we know? It has kind of a bleachy type of odor. You probably haven't really noticed it, although after a good solid thunderstorm with a lot of lightning, you will notice a certain smell in the air, and part of that smell is ozone. It is toxic, as I mentioned. It's very damaging to lung tissue and things like that. It can also cause headaches, burning in your eyes, right? Your eye tissue is quite sensitive, and irritation to your lungs and your airways. It's also damaging to things like plants or rubber or plastics, or also plants and trees and tires and things like that. I said plants and trees as if trees were not plants. So that's a picture of I think it's an aspen, like a trembling aspen, or, because I know my leaves, maybe it's a cottonwood, or I have no idea what it is. It's a leaf. But it's been damaged by exposure to ozone. And there's a tire, I knew what that one was, that's also been damaged by exposure to ozone, ground level ozone. Now, all of these things are not to say that ozone in the ozone layer is bad, because we definitely want ozone in the ozone layer, but ozone in ground level areas is definitely not something we want. So, ozone layer, what's going on there? Well, for that, you're going to have to go way up into the atmosphere, into what's called the stratosphere. And it's higher than airplanes fly and so on, things like that. It's way up there. But you can see where the ozone layer is. Now, the ozone layer is not necessarily a layer, it's just where the ozone amount gets at its highest concentration. It's still a very small amount, but it blocks out ultraviolet light, and ultraviolet light is damaging to us as well. So whenever somebody says, oh, don't get a sunburn or put some sunblock on, they're worried about ultraviolet light causing damage to your tissues. Okay? UVC doesn't reach down to us. UVB does, and it was estimated that a 5% decrease in ozone could lead to a 20% increase in skin cancers. So what does ozone do to protect us? Well, ozone does 2 things, right? There's ways of making ozone, and there's ways of breaking ozone, and that's what's called the ozone cycle. So a molecule of oxygen, 2 atoms of oxygen bonded together, breaks when it absorbs ultraviolet light and forms 2 atoms. One of those atoms goes off and reacts with an oxygen molecule to produce an ozone molecule. So that's making ozone. That's how we get it. Well, part of ozone's job is to be broken. And where ozone can absorb ultraviolet light and make oxygen molecules and oxygen atoms, and then one of those oxygen atoms could also react with an ozone molecule to make 2 molecules of oxygen. Now, the thing about that cycle is it just keeps repeating, going back and forth. As long as the lights are on, right? Because both of those require ultraviolet light. You get to the dark side of the earth, nighttime, or wintertime for that matter, where there's not as much light available, and those reactions are going to stop. And everything was working pretty well until we realized that the ozone concentration in the ozone layer was actually getting kind of small. So then they realized that there were other things that could be involved in ozone destruction. And one of the culprits was chlorofluorocarbons, CFCs, which we also sometimes call freons. And we still use that term, even though they kind of refer to different things now. Whew, what's a chlorofluorocarbon? Well, they've been around for a long time, and they were seen at the time and for a long time as being really ideal, perfect chemicals because they were cheap and effective and non-toxic. So we could use them in all kinds of places without worrying about certain problems. And we did use them in a bunch of places. Refrigerators and air conditioners, we used them in aerosol propellants, and we used them in blowing foam. So if you were trying to make a nice soft cushion. Okay, but then we found out that there was a bit of an atmospheric problem. Now the whole investigation started when they noticed that the ozone layer was being broken, or ozone was being broken without being regenerated. So the four normal reactions involve breaking ozone, but also making ozone. And if you can't make ozone, but you can break it, well, eventually you're going to run into a problem. So they found out that CFCs, and there were several of them, I've just picked one of them here, will break a chlorine atom off. And that chlorine atom can go out there and it can react with ozone to produce this other thing. And then that thing can react with the oxygen atom to produce other things. Now, two things that are important. Number one is that reactions 2 and 3 continue when the lights are off, wintertime, at night. And second thing is reaction 3 makes the thing that can go out and break ozone. So 2 and 3 keep going, keep going, keep going, keep regenerating the problem piece that breaks ozone. Okay, a little bit more history. I know we've been doing a lot of history. 1970 was a good year. 1970 was a good year, unless you're talking about fashion, then it was a terrible year. But because of increased space travel and air travel, they thought, look, what's going on in the upper atmosphere? We better look into this. So they did a study, and they discovered that the chlorine in the atmosphere was able to and was destroying ozone. Then they wanted to figure out where that chlorine was coming from. So they predicted that, or they figured out that the chlorine from the CFCs was going to be probably the biggest and most concerning source, because we were making thousands of tons of CFCs every year. 1975, not a bad year. Government panel came out and said that we need to do something about this. In fact, they recommended that we actually ban CFCs, which was really quite remarkable because it's not normally how they do things. Reduce, sure. Eliminate, that was pretty amazing. But 1975, they said we should eliminate CFCs. Keep that number in your head, 1975. Now, pretty simple statement, hard to follow through on there. So the aerosol industry was making the propellants, was making the foam blowing things. They started a campaign to, well, resist that, but also to what they wanted to do, or what they said what they wanted to do, was educate the public. Really what they wanted to do is tell the public the other side. And they made certain claims. They made claims like that human activity cannot possibly damage the atmosphere. So there's nothing that humans can do that is big enough to damage the atmosphere. And at this point, I want to pause and just look at some scenery, like Los Angeles, Beijing, China, Mexico City, Toronto. What was I talking about? Oh yeah. People can't damage the atmosphere. It's actually not true. We can. Now those are pictures of smog, which do actually end up making some ground level ozone, but that's beside the point. They blame volcanoes, like the one in Toronto. You may recall when we were talking about acid rain, they were also blaming volcanoes for the sulfur in the air that was coming down, or the sulfur dioxide that was coming down as acid rain. So volcanoes are really bad. Like, they're just causing all the problems. They also claimed that the science was flawed and the science was incomplete, and they never really said why the science was flawed. They just said that it was. I don't know if they ever thought that they needed to show what the flaws were. And then they said that the delays in reports were actually things that said that there was no problem at all with the CFCs. Now here's the thing. The delays in the reports came out later because the scientists were trying to get rid of any flaws and to make the science as complete as possible, which was what they wanted, except then it turned out to be, they were accused of something else. And then the same people that were opposed to doing anything at all, they were opposed to flaws in the science. They turned around and they were making actually false claims about the data and about some of the conclusions that were happening. And in the meantime, the science was just trying to get the reports right. Okay, 1985, so 10 years later, British researchers found what they called was a ozone hole. So not just an ozone fin, but an ozone hole. Very low ozone concentration over the South Pole. And that's a picture of it in 1985, where the more red it is, the less ozone there is. And then it goes out to be, well, I don't know about normal, but it looks like that. Now, here's the thing about the South Pole. There's not a lot of air conditioners at the South Pole, and there's not a lot of people using hairspray. So the release of CFCs at the South Pole is pretty much non-existent. So the CFCs got there somehow. Okay, so the concentration was much lower than any of the predictions. So here's the deal. The science was flawed because reality was worse than what the science thought, not the other way around. 1987, they put together an expedition to go to the South Pole and try and figure out what was going on with atmospheric conditions, with CFCs, with the ozone. Right? What was the problem now? Okay, we're going to jump ahead. Okay. There's an ongoing resistance to regulations, which was eventually they managed to regulate the things anyhow. There was an ongoing false claims about the problem, misrepresenting the scientific data. People just didn't want to listen to what was going on. They didn't want to hear the scientists. They wanted to believe their own thing. 1996, so, well, almost 10 years after the expedition to the South Pole, CFCs were finally phased out and replaced worldwide, but here's the problem. Up until that point, they were still being used, which means they were still out there, still being released. So in 1996, the South Pole ozone hole was quite a bit larger. 10 years later, in 2006, it was about the same size. It moves around a little bit, but you'll notice that it's still quite a bit still quite large, and it doesn't seem to be getting a whole lot better. But time goes on. So now we're many years past that. So 1996, the CFCs were finally phased out. The ozone hole, or thinning, in the South Pole does seem now to be patching, fixing, filling in. Okay, I do want to make a couple final comments. Number one, science is always going to be incomplete. Science is always going to be a little bit less than perfect, or I shouldn't say that. I don't want to use the word flawed. It's not going to be flawed, but it's never going to be perfect, and it's never going to be complete. But then the question becomes is, what standard are you going to reach before you do something? And then oftentimes inaction, doing nothing, isn't really an option. We need to do something. Anyway, we'll kind of pick this up with some other stuff in a little bit, and it doesn't necessarily lead us into a place to talk about current environmental issues, but we'll do that another time. Anyway, thank you for watching.